Do some chemistry with me while my apartment gets destroyed by Hurricane Milton. This compound has 2 carbon atoms and 4 hydrogen atoms, so we can draw it like this. Now let's try to find each of these carbons' hybridizations. We just do that by counting the steric number. So for this carbon, that's bonded to 1, 2, 3 things, so that's sp2 hybridized. How about the other carbon? Same thing, 1, 2, 3. So that's sp2 hybridized. I'm going to redraw this molecule so that we can look at its atomic orbitals and hybridization orbitals. So each of these hydrogens has an s orbital. It's kind of spherical in shape, and that's because the electron configuration of hydrogen is 1s1. And these carbon atoms each have this sort of long orbital, and that's the hybridized sp2 orbital coming off of it to form each of these bonds, these single bonds. The carbon-hydrogen single bond, the carbon-carbon single bond. And so when these orbitals make direct contact with other orbitals, they make sigma bonds. And there's 1 sigma bond per single bond. Now, there's these other orbitals coming off the carbon that sort of jut up and down, above the carbon and below the carbon. And they don't directly make contact with each other, but there's sort of like an overlap. And so since these bonds are made from p orbitals, they're called pi bonds. Some molecules have atoms which have lone pairs in p orbitals that can move around and can even form new double bonds or pi bonds. So when molecules can do this, they can form alternate structures. Those are called resonance structures. And this compound is one such example. It seems like there's a negative charge in the oxygen and a positive in the carbon, meaning there's an area of generally high electron density near the oxygen and an area of low electron density near the carbon. So one of the lone pairs on that oxygen can delocalize and participate in resonance, right? It can go down just like that and form a double bond. So we can draw the resonance structure like this. The bottom part stays the same because no electrons are moving there. But this oxygen is now double bonded to this carbon. And so that means it has 2 lone pairs left. And what's so good about this structure is that it gets rid of all the charges, right? It gets rid of that negative charge because the oxygen's octet is satisfied. And it also gets rid of that positive charge because the carbon's octet is satisfied. And because there are no charges and the octets are all satisfied, we would consider the resonance structure on the right to be more significant. This is water. And this is ammonia. Now, which one's a better acid? Well, we can compare which one's a better acid by comparing the conjugate bases. So if we strip 1 acidic proton off of each compound, we can make its conjugate base. This oxygen now receives a lone pair and a negative charge, and the same happens with the nitrogen. Right, it receives a lone pair and a negative charge. Now, let's see where the negative charge is on each atom. This one has it on the oxygen, and that is more electronegative than the nitrogen, meaning it better stabilizes that negative charge, meaning it's a more stable conjugate base. And because it's a more stable conjugate base, that means that water is a better acid because it produces a worse or more stable conjugate base, hydroxide. This is a compound. It has a 4-carbon alkane backbone and a hydroxyl group, so we can name it butan-2-ol because the hydroxyl group is on the 2nd position. But that isn't all to the name of this compound because if we draw that invisible hydrogen that's not shown on bond line structures, we see that it's bonded to a hydroxyl, a hydrogen, this ethyl substituent, and this methyl substituent, which means that it's bonded to 1, 2, 3 things, all of which are unique substituents, meaning this compound has a stereogenic center. And stereogenic centers can have one of 2 configurations, either R or S. How do we figure that out? Well, we have to assign priorities to each of these substituents, and priority is based on the atomic number of the atom that stereogenic center is bonded to in each of those groups. Let's go back to this original slide and assign priorities. First, let's redraw that invisible hydrogen. And of the things that stereogenic center is bonded to, oxygen has the highest atomic number, and hydrogen has the lowest, so we can give those 1 and 4. How about to do carbon atoms? We can give the carbon atom on the right 2, and the one on the left 3. Why? Let's draw out what things that carbon atom is bonded to. It's bonded to a carbon atom, a hydrogen atom, and another hydrogen atom. The one on the left is only bonded to 1 carbon atom, and then it's bonded to 3 hydrogen atoms. So the one on the right wins, and we can give it 2. Let's count from 1 to 2 to 3, either clockwise or anti-clockwise. If we draw the arrow, that's going clockwise. So this stereogenic center has R configuration. We can combine the two to make a new name, the real name, R-butan-2-ol.